So the Nissan Leaf, probably from the factory, can pull about 0.7 G. So that means that the centripetal acceleration is 70% of gravity. Well, if it's 70% of gravity and it's on this circle, we know that this circle has a radius of 32 feet. So 0.7 G is an acceleration. Gravity is acceleration, so we just have 70% of gravity, so that's our centripetal acceleration, is equal to v squared over r. We know that gravity is equal to 32 feet per second. So 0.7 times 32 feet per second squared. 0.7 times 32 is 22.4. So now we have v squared over r equals 22.4. We know r, it's again 32. That leaves us with v squared equals 717. Square root of that, 26.7. The velocity is equal to 26.7. And what are our units? Feet per second. Well, that's not terribly useful because we don't usually talk about cars going feet per second. So to continue on, the velocity is equal to 26.7 feet per second, and we want to convert that into miles per hour like we did before. So we want to get rid of the feet, so we're going to put it opposite so they cancel, and we want miles. So 1 mile is 5,280 feet times seconds. We want to get rid of seconds, and we want hours. So we'll put the seconds on the top to cancel this second. Hours on the bottom. 1 hour is equal to 60 times 60, 3,600 seconds. So 26.7 divided by 5280 times 3,600 will be our velocity in miles per hour. Divided by 5280 times 3,600. V equals 18.25 miles per hour. So, if the Nissan Leaf is achieving 0.7 Gs on the skid pad, that means that it can effectively go around this circle of 200 feet circumference, a circle of radius 32, they paint a line on the ground, it can go around this at 18.25 miles an hour. It doesn't seem very fast, but a lot of corners like freeway off-ramps, you have to slow down quite a bit to make it around. The fastest, highest performing cars can pull 1 or more Gs on the skid pad, like 1.05. So if we imagine a car that's turning a little bit bigger than 1 on the skid pad, then if you think about it, if it was exactly 1 on the skid pad, then the person in the seat would feel pushed down into their seat, and they would feel pushed right out of their seat at exactly the same amount. So if you can get away from the sensation of motion, in that moment, if the car were tipped on its side, it would feel exactly the same. The force of the car sideways, I am unable to draw a car tipped sideways, so the back window here and tail lights. So if it's tipped sideways like this, these are the tires, the person in there has the sense of gravity pulling them down at what? 1 G. Gravity is 1 G. Another way to look at it is if the car is going around at 1 G, it is the weight of the car pushing down on the concrete is the same as the car pushing sideways. It's the same. G-forces in a car are the felt sensation, which is really our body wanting to stay either in motion or at rest. When your body wants to stay in motion, it means that it does not want to turn. Your body, again, this is a tangent line. It just touches the outside of the circle. Your body wants to go along this straight line. If you're going along in a straight line at 60 miles an hour, and the car is smooth and the road is smooth, you could for a minute forget that you're in motion. Now, what you feel is the bending of this, the acceleration, the force that makes you turn. Here's a straw. In order to turn, the force has to be applied toward the center. Now, where this, the real punchline of this is, when you're on the merry-go-round, this person on the merry-go-round, it's spinning this way. You know that the force that you seem to feel that is pulling you off, you know that that force is not real because what happens when you let go? When you let go, you do not go in the direction of these arrows. So again, I'll draw the merry-go-round. I will draw the person just with their head. If they're going around and around, you feel, I feel like they're being thrown off the merry-go-round in that direction. The force is actually toward the center of rotation, or the axis of rotation, that point about which it rotates around. The green is actually the force, or the acceleration, the actual one. So I'll say force centripetal. And I'm going back and forth between force and acceleration. They are proportional, but we hear people talk about g forces, not g accelerations. So that's the only reason I go back and forth between force and acceleration. So there is a force pulling the person toward the center, and it is actually against their hands on the merry-go-round and their feet. That's where the forces are actually applied. Now, as it's going around, right when it reaches this point, if you let go, what happens? If this were a real force, if the red one was, when you let go, your body would move in the direction of the force. But that's not what happens. If you're on a merry-go-round or anything else spinning, and at that moment of time, you are released, whether you're spinning a weight around on a string and the string, if you're spinning around and at that moment you are released from the rotation, or if you're spinning a weight around on a string and the string breaks, you do not fly off the merry-go-round in this direction. You fly off in this direction. Because at that moment, you have a velocity. And the velocity is tangent to the rotation. Tangent, like this green line is tangent. That is your velocity at that moment. Objects in motion stay in motion. The motion that you are in is in that direction. The only reason that you go in a circle is because there's a force applied to you that keeps turning you around and around. So we would call, the red is actually called the g-force. And we could figure out how fast you would have to spin on a diameter 10 feet merry-go-round, how fast you would have to spin in order to obtain one g-force, or 1g. But the moment you let go, you do not fly out radially, you fly forward tangentially. So that is the evidence, the proof, that g-forces are not real, they are the effect, you feel it. That centrifugal force is not real, it is an effect, you feel it. So we have a skid pad. Again, if the car breaks loose, which means the front tires start to slide, the car is not going to shoot off in this direction. It's going to spin off in this direction. All right, finally, fighter jets. That's where all the talk really about g-forces come in, because jets can do some absolutely incredible maneuvers. When they're accelerating, the pilot is pushed back in the seat. When they make a left turn, they're pushed to the right in their seat. When they go up, they're pushed down and back in their seat. When they go down, they're lunged up into their harness. The forces exerted upon the pilot, because the airplane can move so fast, I mean, a whole lot faster than 18 miles an hour around a skid pad, can move so fast that they had trouble with the pilots losing circulation. So here's the pilot, and he has a joystick, not a steering wheel, in the jet. I don't know what he does with his other hand. Turn signals. The forces were so great that the blood would rush down to their feet, and their feet would swell up, and their legs would swell up. And if your legs and feet fill up with blood, where did it come from? It came from your upper body. Let's say you're half empty up here in your brain. So pilots would pass out. And when you're flying a plane, you don't want to pass out. That's bad. So they realized that the forces that fighter jets can reach are between 7 and 9 Gs. So that's 7 to 9 times as strong as the force of gravity. 7 to 9 times faster acceleration. So if you were standing up, on Earth, that's 1 G. 7 G would be 6 other people standing on your head. That's how much pressure would be where your feet meet the ground. And so pilots wear special suits, G suits, and they're very tight fitting. That's not exactly true. They're fixed and fit. So they're not necessarily tight, but if your leg begins to swell up, they will not allow your leg to swell up anymore. And so they keep the suit keeps your body from swelling up. If your body in your extremities cannot swell, then the blood can't leave your vital organs in your brain. That's it for Flat Math 103. Centrifugal force, acceleration, and now I believe we can finally get into what's happening with hot air balloons, weather balloons, airplanes, etc. Thank you for watching.